really put me in the mindset of like, or not in the mindset, but it really put me down to like, okay, I really need to get how all this like builds up, like very
Yeah.
formally and specifically.
Right.
So
Yeah.
I
He does a nice job of like the first half of the last century, right? Hey, Eli, how you doing?
Yeah, I even got to find.
I am actually kind of sick right now, so.
Sorry, I couldn't hear.
Let's see. Is this actually?
Let me turn.
Can you hear me now?
Yeah, that's good.
I'm actually pretty sick right now, so I'm probably gonna turn off my camera. Otherwise, you'll see me.
Oh, geez. Yeah, you're looking a bit pale.
Yeah. So, other than that, I'm doing okay. Just pretty under the weather right now.
Yeah, sorry to hear you're under the weather. Let's see. What is that? Yeah. Hi, Kevin. How you doing?
Doing great.
Yeah, I'm struggling with a new computer here. I didn't have everything set up, so I had to download Zoom. And yeah, okay. So there we go. I think I've got everything working. Let's see. We're missing Tyler, I guess. Yeah, I was lucky to get here before too, because I, booted up and didn't have Zoom installed, so I had to go get Zoom and all of that. Oh, Oreos. Oh yeah. Yeah. You still up for a Zoom tomorrow, Eli?
Yeah, I should be able to. That'd be fine with me.
Okay. Yeah, if it gets a bit much, we can push it back, but let's give it a try. Okay, so let me see where we are here. Gauge theory. And last time we went through the initial approach, the standard early approach to gauge theory. Let's see, I'm recording, I got markers. Okay, we're good. So what people used to do, let's see, can you see me here? There we go. You'd have an action functional, a Lagrangian, and it would have some global symmetry. And for whatever motivation, you would try to extend that to a local symmetry. And you find you can if you simply introduce a connection. And that connection is something that is, let's call it omega, that contracts on a group generator, which makes it an element of the Lie algebra. It also has a space-time index, which we can use and put a basis on and make it a one form. And now this connection, omega, is a Lie algebra valued one form. And connections are always Lie algebra valued one forms. What they're telling you is, right, these are infinitesimal generators for some Lie group symmetry. So if I have a local, the ability to do local transformations, what this is telling me is when I go through the displacement dx mu, I need to adjust to the new gauge, the new choice of group element. And so I do an infinitesimal, because we're moving infinitesimally, we only need an infinitesimal group transformation in order to get in the right gauge. So that's how the connection works. It puts us in the new basis at the adjacent tangent space or group space. Now, a more general picture of what's happening here has gradually emerged and is used quite often these days. What we have is, well, certainly space-time. And a way to think of the gauge symmetry is to imagine a copy of the symmetry group at each point. So these lines represent, oh, let's say SU3. So at each point of the space-time manifold, so we've got some four-dimensional space-time, Minkowski space here. At each point of this, we have a copy of the gauge group. So what choosing a gauge amounts to is picking a point on each of these fibers. Now, the word is fiber. We're building a fiber bundle here. But SU3, that's an 8-dimensional group, right? So we're attaching, at each point of this manifold, we're attaching some 8-dimensional group. That's the big thing. You guys have seen this before. Okay, you've had general relativity, I think, right? We talked about it. Okay, so there's a tangent space. If you want to talk about vectors on a curved manifold, like the surface of an apple, what you do is at each point of the surface of the apple, you attach a plane. And you can have vectors in that plane, and each of those vectors is a tangent vector to some curve that's following around the skin of the apple. In fact, you can think of that tangent plane as the set of equivalence classes of all curves passing through a given point on the surface of the apple. And those tangent vectors lie in a plane because they're vectors. You can add them, you can do whatever you like with them as vectors. So we're doing a similar thing here. Instead of taking our apple and attaching a plane at each point so that we can talk about tangent vectors to curves on the apple. Now we're going to attach whatever group we like, whatever object we like, right? There are all kinds of fiber bundles, right? A fiber bundle in its most general sense is the attachment of any object you like. It could be a vector space, it could be a group, it could be any sort of mathematical object. You attach a copy at each point of your manifold and you have that kind of a bundle. Let's see, so, well, there are more general objects than groups or semi-groups or tangent planes, but
we can be restrictive and just look at vector bundles, right? Vector fiber bundles.
we can, and that's enough for tangent bundles, right? The tangent space or the cotangent space, those are vector bundles. You've attached a vector space at each point, right? What we're doing is called a principal fiber bundle. CIPAL. And you see this spelled RE or ER, RE being the British spelling, but and either one depends how classy you're feeling, I guess, which way to spell it. You can alternate, doesn't matter, it's fine. But principal fiber bundle was basically the first kind that Carton built ages ago. What he was doing is classifying groups and trying to construct geometries and find properties of geometries. And the principal fiber bundle is one where you have a lead group attached at each point of the manifold. And that's the kind that we're going to be interested in for gauge theory. Now, let's see, how do we do this? Let me back up to the choice of the gauge. I was starting to say, all right, so on each of these fibers, we're going to pick a particular group element to be our full gauge choice. So at each position X here, we're going to have some element of the group. G of X there. And what happens is you end up choosing what's called a cross section of the bundle, right? On each of these fibers, you choose one point, and that's a thing that it's in a one-to-one correspondence, which with what I've drawn is this space-time down here. Now, in fact, because the theories we're writing have local gauge covariance, those two are equivalent, right? We can move these points up and down these fibers, and the this object that we're constructing, all the physics is going to be the same wherever we choose to put the cross section on a given fiber. So we're building a structure that is independent of, it's called lifting. It's independent of moving the points up and down this fiber. Any full cross section like this, including, you know, it's convenient to draw that flat one, but there's nothing special about that flat one. Each of those is a manifold. And the way that Carton built these structures was to start with a group and a subgroup, a Lie group and a Lie subgroup. So suppose we
Sorry,
have,
can you clarify one thing for me?
yes,
When you
Oh.
said that it is a manifold, is the principal fiber bundle a manifold? Is that what you said? Is that what you meant?
okay.
Or the cross section?
The initial parts of this construction, everything's a manifold.
Okay, that's
Right.
nice.
We build this within a Lie group
Which is
for
nice.
starters.
Yeah.
We can change it, so that's a later step. But if we start with a Lie group G and a Lie subgroup H, okay, these are Lie groups. And you may recall a Lie group is, in familiar terms, it's a group that's also a manifold. So these are already manifolds, and everything at first is going to take place inside of the manifold G. That's the whole space. So all of this is going to be G. Here's the way it works. Let's get a fresh picture going here. Yeah, if I'd gotten a smaller board, I'd spend less time erasing. So the let's take a picture of, all right, this is our group G, our big group. Now we have a subgroup. What we can do is take any element of G. All right, so G is some element in G. Now we're going to apply every element of H to that. So we get a point up here, H acting on G. And, you know, another point, H prime acting on G. And by the
So the
time
orbit?
sorry?
So the
Oh.
orbit?
The orbits, yeah, the orbits of H in G. That's right. We do that for every point in G. So we're going to do this for all G. And it's not too hard to show. I mean, we can go through a proof if you like, but if any two of these orbits intersect, they're identical. And it's not too hard to see how that works. Suppose we have two that intersect. Well, you know, we've got the orbits. The orbits are also called cosets. So the coset of this G is that orbit, or that is going to be a fiber. Right. If two cosets intersect, so suppose we have G1 and G2 here, and this is H of G1 and H of G2. All right, so this is the curve I get inside of G by applying every element of H to G1. Here I apply every element of H to G2. Suppose those two intersect. Then G1 times there's some H1 G1 that gives me that point. But H1 G1, there's also some H2 G2 that gives me that same point if they intersect in any point. But H is a group. So that tells me that G2 is equal to H2 inverse H1 G1. This is some other element of H, and therefore G2 lies in H of G1. And you work the argument the other way, and you see that G1 lies in H of G2. They're the same set. Pick any elements here, you can find some H that relates them. It's not hard now to see how that's going to work. You know, try a detailed proof. It's good exercise. So these are all disjoint. The cosets are disjoint. They also are space filling. We know that because we can form a coset for any G in all of the whole group. So if we've formed a coset from every single G, then clearly there's a coset containing every point of the whole group. And those are disjoint subsets, and each of them is isomorphic to the original group H. There's exactly one element in each of these for each element of the subgroup H. So then we do a bit more work with this. It's not too hard to show that just by definitions that we have a fiber bundle. Let's see what you do. You know that G is a manifold, and so you have charts on G. You've got maps into Rn. Okay, so you have a way of labeling all the elements of G with some coordinates. You can adapt those coordinates. So if you want X alpha to be the coordinates for some element of G, X1, X2, up to Xn. Sorry, get this. Is this showing up right? It looks backwards to me. Is what's on the board correct for you?
Yeah, everything's good.
Yeah, okay.
It's fine for us.
Yeah, I look at it and I wonder if I haven't configured my zoom yet. That's probably the issue.
Yeah, for
Let's
some
see.
reason it defaults to flipping your own view, but
Yeah,
seem
let's see.
fine.
Sorry, what is it? What's the setting to?
Probably mirror. Something about mirroring your image.
Yeah. I'm looking for it. Is it on the bottom?
Oh, setting video. If you go to where it says stop video, you click at the arrow video settings and it says mirror my video. You can deselect that. And that might help. Yeah.
Oh, okay. Probably preferences.
Sure.
Video.
Yep.
Mirror my video. Yeah. Okay. Let's not. And then I'm seeing. Okay, that's better. Now I'm seeing what you're seeing. It was weird to look here and it's all backwards. Okay. So here are coordinates. But what you can do, since H is also a group and therefore a manifold, you can choose the first. Suppose the dimension of H is K and the dimension of G is N. You can choose, let's call them Y, Y1 through YK, the first K elements here, to be coordinates on the fibers, because each fiber is a submanifold, so we can put coordinates on it. And then there are xk plus 1, well, yeah, sure, up to xn. The remaining coordinates are coordinates across through the fibers. So if you you could hold the Wise constant and span a manifold going across this way. So basically, you're choosing one point from each fiber. It's a cross section. You do that in a smooth enough way, and you can prove that the quotient of a Lie group by a Lie subgroup is a manifold with dimension. Well, I'll just write n minus k. It's the dimension of the difference of the dimensions of G and H. So the main property that you need in order to have a fiber bundle is a projection. And basically our projection here, this manifold consists of how to say that, it's the set of all independent cosets. And so you can choose any representative, any particular point on a coset and work with that, but everything we do is going to be invariant under moving up and down that fiber. So where was I here? So the set of cosets is a manifold. And so the projection, our projection from G into the manifold simply takes any element G of the big group and assigns it to its coset. And that's a point in the manifold. So that is a projection from the fibers to the manifold. It's an abstract way to characterize a manifold, right? Each point is this whole group thing. It's a little backwards from the way we like to think about a fiber bundle list. Okay, we've got a manifold. Now we're going to put fiber through each point, but it's equivalent.
But this is like looking at the Lie group itself. But what we're dealing with is like a space-time and then a Lie group acting on that space-time, aren't we? Or am I?
No, we're going to get there. No, we're doing group theory here, pure and simple, right? From the group theory, from a Lie group and a Lie subgroup, we've constructed a manifold. That's going to be space-time.
Oh, okay. I
Right?
see that.
That manifold
Okay.
will be space-time, and
Okay.
yeah, we can even take the time to prove it. That's yeah, we'll see how much of this we want to go into detailed proofs of. A lot of the proofs of these things are in the Gage Theory book, and on the Canvas page for this class, along with the quantum field theory book, I have linked the Gage Theory book. And I just want to check that I have, yeah, I've published that. So if you've misplaced your link to the Gage Theory book, I've placed it on the Canvas site for the Quantum Field Theory Club. I lay out this method in detail there. I probably improve all these results. I forget whether I proved all of them or not, but one can. This is what Carton did. He showed that you could produce manifolds by taking quotients of groups, and this led to a large classification of manifolds. He'd already classified groups, so Lie groups. So having Lie groups at his disposal, he was able to construct this wide range of manifolds. Now, we're interested in a fairly simple manifold, R4 with the Minkowski metric on it, just space-time. There are methods to produce curved manifolds. So let's have a look at how we do all this. There's there's a different way to write the Lie algebra. Have you guys ever seen the Carton equations? Are you familiar with those? No. Okay. Are you reasonably comfortable with differential forms? Maybe. So the Gage Theory book has a chapter on differential forms. It's about 30 pages. Can refresh what you might dimly remember from somewhere, or it's got all the basic properties, so you can learn differential forms there. But I would like to use them for this chapter. This isn't completely necessary to understanding the standard model, but it does put it in a really nice context. So I want to show you this development. If we start with the Lie algebra, we have generators, GA, GB, giving some real structure constants. And I have stressed in the text and probably in class the difference between Hermitian generators and real structure constants. Those are often in conflict. It's very convenient when doing quantum things to work using Hermitian generators, but the typical symmetries actually have antisymmetric, or sorry, have anti-Hermitian generators. The commutator of two anti-Hermitian generators is a real structure constant times an anti-Hermitian generator. You'll see a lot of explicit I's in the structure constants for the unitary groups. That's because people are using Hermitian generators. So if I have the, Russ, this is going to be awkward. If I have Hermitian generators with some structure constants, well, it's probably going to be an I, CAB, HC here. Now, if I multiply everything by I, two factors of I over here, a factor of I here, and a factor of I there. Now I have anti-Hermitian generators here. That's an anti-Hermitian generator, and that I goes away. I just get a sign. So if I want real structure constants, then I adjust the generators appropriately. So there really are anti-Hermitian. If you're using Hermitian generators and want to get the group elements, you've seen this with SU2, e to the I phi over 2 n dot sigma. Those polymatrices are Hermitian. We have to have an I here to make it anti-Hermitian. It is anti-Hermitian or antisymmetric transformations that preserve a Hermitian or real metric. And so rotations always involve anti-Hermitian generators. So this is an element of SU2. All right. What I want to stick to for this discussion is real structure constants, because the structure constants are going to become part of our geometry. So if we need to, we multiply our generators by I or something so that the structure constants are real. Okay, here we are, the Lie algebra. I want to write the Lie algebra in a different way. I can always write the Lie algebra generators are basis vectors. The Lie algebra is a vector space. And so these are basis vectors. And vector space, we can introduce some coordinates. So G is some sort of a vector in this sense. Tangent vector to the group manifold, in fact. vectors are dual to one forms. So there's a natural way of combining a one form and a tangent vector to give a chronicle. So given any tangent vector, I can write a one form. Given a one form, I can write a tangent vector. And the trick then is to write these vectors in terms of differential forms. So what I do is I asked for some one forms that are dual in this sense to the generators of the algebra. So I want a delta AB here. And because these are linear combinations of these basis forms, that says, all right, if I, let's see, I want to use an n-dimensional representation for an n-dimensional algebra. That lets me make these into square matrices. So I can write G as some square matrix with some kind of coordinates xm, and I can expand omega as some kind of a matrix as a one form, dxn. And if I then impose that these one forms are dual to those tangent vectors, the linearity of this product tells me that GBM omega in A with the inner product of ddxm dxn, this is a Kronecker NM. And that's got to be delta AB. This contracts the M and the N, so GBM omega MA has to be Kronecker AB. And that tells me that the coefficients that I use for the one forms are just the inverse matrices to the coefficients I use for the vectors. How you doing here? You good? Yeah, jump in with questions if it's this is a lot of formal stuff kind of fast, and it's a little bit of field from the field theory, but
I still need to see the bottom of the board yet, though.
Oh. Yeah, sorry. Yeah, this this new screen is a bit stiffer than the old one. Okay, there you go. There.
It's all good here. Just a little. So I have a question.
Yeah.
This is more of just like the canonical going one from the other, right?
Yeah. This is the canonical. Yeah.
But when we do like
forms and vectors,
Yeah.
if, on manifolds, you've got a cotangent space and a tangent space. This is the relationship between them.
Right. But when you have something like space-time, you don't pick this canonical relation, right? You pick it via the metric. Isn't that true?
You can, right? So yeah, the metric gives you inner products between these things. So d dx alpha d dx beta. There's an inner product on these things. That's the metric. And the dx's in a coordinate basis, the dx's have the same thing with the inverse metric. So you use the metric in general relativity. You use the metric to give a relationship between these two. So if I have the components of any one form like this, so I've got these VI's, I can use the inverse metric to produce a unique tangent vector Vj. Right? The up and down indices correspond to this. So these are forms, those are vectors. They're completely equivalent. There's a one-to-one onto map between them if you have a metric. And that's the one we generally choose. I'm going a slightly different direction here. So what I want to do is rewrite the Lie algebra in terms of these guys. And it's straightforward to do. You write this out, putting in these derivatives. Let's just do it. Nice. I could talk you through it and you get the gist, or we can do it and then we've done it. So let's just do it. I'm going to write this in this basis. Now, an n-dimensional matrix representation for an n-dimensional Lie group is given by the adjoint representation, right? Where you actually use the structure constants as these matrices. So G, B, M would be, let's see, no, how would I say it? So yeah, if I have GA and I want the BC components, I can take that to be C, BAC, like that. It turns out you have to go through and prove this, but this actually does give the right commutation relations and the Jacobi identity. In fact, writing the Jacobi identity in terms of these guys shows that they satisfy the commutators. Yeah, it's kind of cool. It's always a representation for a Lie group. So we can choose that one if we like, and that'll be the right dimension. So this always exists. So what I want to do is write GA M partial
Small
M.
question,
Yeah.
just to make sure the Lie bracket that's associated with the infinitesimal generators, that's the standard Lie bracket that's associated with vector fields, right?
Yeah. These are vectors. Any vector in the Lie algebra can be expanded in terms of these. So there's a bracket for every pair of vectors in the Lie algebra.
Gotcha. Okay, just want to make sure. Thank you.
Yeah, sure. So let's, we can write out what this commutator is. It's G A M partial M G B N B N minus the other way around, G B, let me use M here, D M of G A N B N. So I can prove it. So this is the coefficient of some vector, and in fact it's C CAB GC N partial M. So this becomes the Lie algebra written in painfully explicit vector form. I can take off these basis vectors, and now I have, I don't know, sort of a Wronskian thing on the G's. This G times the derivative of that minus the other way around is linear in those coefficients. Now, all you have to do then is, since these matrices are inverse to one another, you just whack that expression with the inverse matrices on every free index. So I've got G A M partial M G B N minus G B N M partial M G A N equals CAD G C N. Okay, so now if I put omega, let's see what indices can I use here? All right, let's use P A omega Q B. Omega P, whoops. P A omega Q B. So I'm going to put that on both sides. And now this one with that one gives a delta MP. And then we have omega Q B partial M G B N. And then here, the B on this one gives a Kronecker MQ. And then we have omega P A partial M G N or A N. Equal to that stuff up there. Let me just work on this side for the moment. Now, this thing I can write as partial M of the product omega QB GBN minus partial M omega QB times GBN. Fair enough? Just product rule. But this is a Kronecker delta, so its derivative is 0. So I basically can integrate by parts to just a minus sign here. And now, doing that on both of these terms, okay, this, I have a Kronecker MPs, that's going to become a P. So I have minus partial P omega Q B G B N. And then this one is going to become plus, changes the sign. Then we'll have partial Q omega P A with G A N. All of that is equal to this side, C CAB omega P A omega Q B on a G C N. Okay, we on the same page here? Question about it? Okay, so now I've got one more G to get rid of. Each G has a free N index. So I'm going to multiply by an omega N. Let's see, what haven't I used? Better make it a D. Okay, that's going to give me a Kronecker BD here. So I have minus partial P, oops, omega Q, this is going to become D, plus partial Q omega P, and I get a Kronecker AD with this omega on that G. So this becomes a D as well. Then on this side, I have a structure constant CAB. Then omega P A omega Q B. And now the omega ND gives me a Kronecker DC that's going to change this C to a D. And now I've expressed the commutator of the Lie algebra, the Lie algebra product in terms of the dual one forms, the omegas. Now, nice thing about this expression, it's antisymmetric in PQ. Right here, the structure constant's antisymmetric in AB, and each is contracted on an omega, which imposes the antisymmetry under the PQ on this side. On this side, it's explicitly antisymmetric on PQ. So I can put a two-form basis, dx p wedge dx q, onto the whole equation without losing anything. So I can write everything in terms of differential forms. Okay to erase here? So I'm going to put a two-form basis. This wedge product, recall or know now, is antisymmetric. It's the direct product antisymmetrized. So now something to notice is if I take the exterior derivative of omega d. All right, so this derivative is it's a partial derivative with a basis form. So it's a form value derivative, and this omega is omega n dx n. And this operator on d gives 0. D squared is always identically 0. So this partial only sees those coefficients. So what we get is a two form, partial m of omega n d dx m wedge dx n. But that's exactly the form we're going to get down here when we put on a dxp wedge dxq. We just have to keep track of signs and factors. Signs and factors of 2. It's always about that, right? So if I put a dxp wedge dxq on this, that's going to be the same as this. The m is first, the n is second. Here the p is first, the q is second. I have a minus sign. So I can write this first term with those basis guys simply as the exterior derivative of omega d. This one, same thing, except q comes first and p after. So if I interchange these two forms, so q's on the q and p's on the p in that order, I get another minus sign. So I'm going to get another d omega d. On the other side, structure constant is perfectly happy. Then I get omega p a dxp wedge omega q b dxq. It just turns those back into the original one forms. So this is omega a wedge omega b. And what we have then is d omega d is equal to minus a half c d a b omega a wedge omega b. And that is the Maurer-Carton equation. It is completely equivalent to the Lie bracket, only it's a differential equation, which is actually rather nice. We know how to integrate things. So this equation contains all the information of the Lie bracket. It gets even cooler than that because there's an integrability condition that has to be satisfied by differential equations. And in fact, you can always get it from the Poincare lemma, d squared equals 0. If I apply a second exterior derivative to this equation, this side vanishes. Here I get a d omega and another d omega, and I can substitute this equation back in. What I get is the Jacobi identity. So the integrability condition for the Lie bracket is the Jacobi identity. And this is the easiest way to prove that. So everything about the Lie algebra that makes it a Lie algebra is implicit in that one equation, the Maurer-Carton equation. Very nice stuff. So all this, you'll never need all this again, except to see that this is the Lie bracket. And take d of this and substitute this back in, and what you get actually is c a b c. Which way does it go? D e c, something like this, anti-symmetrized. When you substitute for d omega again, you're going to get 2 c's, and it'll be a 3-form equation, so it anti-symmetrizes on 3 indices. And that's the Jacobi identity in the adjoint representation. So we can now work with the Carton equation. Okay. Now, there are a couple of things we want to do here with the Carton equation. Having gotten it and it's being so nice and simple looking, we're going to muck it up. What this automatically satisfies is, let's see, gauge transformations. All right, if I let me think a second how this goes. The lead group the Lie algebra, let's say, is invariant under the action of the group. Because if I let G tilde be G, GA, G inverse, where G is any element of the full group, purely G, then G tilde A commutator G tilde B is going to be G, G, A, G inverse, G, GB, G inverse, minus A goes to B. And those just give an identity. So what we get is G times the commutator GA, GB, G inverse. And we know that that is a structure constant CAB. And we get G, GC, G inverse, which is just structure constant GC tilde. So the tilted ones satisfy the same bracket relation. So the Lie algebra is invariant under the group. Now, we can ask then, if we do such a group transformation of G, what happens to omega? And I'm not going to run through the proof of this today, but omega tilde is G omega G inverse minus DG G inverse. It transforms exactly as a connection. So not only have we got a nice two-form expression for the Lie algebra, we now have a connection on the group manifold. It's called the Carton connection, or that might be the Carton connection. So now I'm going to combine the two things I've talked about so far today. We talked about building a fiber bundle by taking a quotient of a lead group by a lead subgroup. And we've managed to write Lie algebras in terms of the Carton equations. I want to do both at once. So probably no better example than the Poincare group as big G and the Lorentz group as the subgroup. So let's see what happens. Now, to write the Carton equations for any group, and you know this is the way I set out on any project that I work on. I use this all the time. You come up with any representation of the group and find the Lie algebra. Knowing the Lie algebra, you have the structure constants. Once you have the structure constants, you can immediately write this, because the only unknown here is these C's. There's some real numbers. for the Poincare group, that's equal to Lorentz and translations. All right, the Lorentz group has commutators that look like, let me see, you know, the commutator of two Lorentz transformations is a doubly anti-symmetrized sum of four generators. So I don't want to write that all out, but if you put it in here, those four all combine. And so if my generators for Lorentz transformations are MAB, those are going to be dual to some one forms that I'll call CD. And I want to get, well, let's see, let's make it A to AC, A to BD, but I have to anti-symmetrize. So delta A could be D and C could be B. It's convenient to put two labels on any kind of rotation or boost generator because all such transformations are operations on a plane. And the two indices are telling you what plane you're looking at. So it's easier to write a rotation matrix with two indices than it is with one. So these are labels for generators. So the Maurer-Cartan equation for the Lorentz group ends up being this, omega CB wedge omega AC, which is a fairly simple thing. Now, the translations all commute. So two translations generated by P just give 0. The only other thing we need to have the whole set is to know what happens with an M and a P. The commutator of a boost or rotation with a translation. And those come out proportional to the translation. I think we get A to BC, omega AD minus, well, let me put a PB here. And I have to anti-symmetrize the AB, so I need a delta AC delta DB with a PB. And that's the Lie bracket for Lorentz transformations and translations. So if I write the Maurer-Cartan equation for, let's keep these guys a little bit different. Oh, I'm looking at the wrong equation. So this tells me the structure constants. The structure constants are built out of the metric and the chronikers. They're just some plus and minus ones. I put those into the Maurer-Cartan, and if my momentum generators, my translation generators are dual to some one forms, let's call them E, like this, then D of E is EB wedge omega AB. And those two equations in the box are the Maurer-Cartan equations for the Poincare group, for the Poincare algebra. Question? You're looking very thoughtful. Guillermo, how about it? You got a question? Can't hear. You're muted.
The P generators, those are from the translations, right?
That's right, yeah. So
Okay.
they commute with one another, but they don't commute with Lorentz.
Yeah, that's fine. Okay.
Okay, so you work through that general equation. So you write the algebra for the Poincare group. Take any representation of the Poincare group you like. Find the infinitesimal generators. You know, one form would be to take the P's to be ddxa, and the M's can be xa partial b minus xb partial a. right? Those generate Lorentz transformations, those generate translations. Find the commutators. All right, you can find the Lie algebra from a simple representation like that. You can rescale it to normalize things the way that seems most convenient. You'll get something like this and the complicated one for the m's. You take the structure constants you get from the Lie algebra and you substitute into the Maurer-Cartan with the -1/2 and the structure constants. The -1/2 is important. And you will get these equations. Okay, promise you, it works. So now, the next thing is to, let's see, I want to think, yeah, let's look at the group quotient. So if I've got Poincare and Lorentz here, then I want to look at the Poincare mod Lorentz. Okay, Poincare, we have 6 Lorentz transformations and 4 translations. Lorentz group has 6. So this is going to give me a 4-dimensional manifold. If I start with the 4-dimensional Poincare group, right? The 4-dimensional, the symmetry of Minkowski space. So then these now describe a fiber bundle on that manifold. And my projection is automatic here because this equation, oh gosh, do you guys know about involutions?
Is there a brief summary of that? I've never heard of it.
Yeah, let me state it. All right, you may have seen it with Lie algebras where if you have a subset of the generators that let's see, close into themselves, you know, that's going to be a
subalgebra.
Yeah, a subalgebra. Let's see, is that? I have to think if that's the equivalent thing. I'm used to thinking of it in differential forms. In differential forms, suppose I have a set of forms, let's call them omega I and omega A. So, you know, k of these and n minus k of those, let's say. But suppose the d omega i's are any one form back into the d omega i's. So there's at least one of these guys in every term on this side. Then we say this equation is in involution, and a whole lot of things follow from the Frobenius theorem from that. This is involution. So these guys are only changing in their own direction. And that means there's an integrable submanifold. So that means there exist, if we have k of these and n minus k of those, there exist k coordinates such that we can write omega, these k forms I can write as omega alpha I dx alpha. Let's call these alpha equals 1 to k. So I can write them in terms of a subset of coordinates such that x alpha equals constant, right? Clearly that implies omega I equals 0. That describes a submanifold, right? The remaining part of the space is a manifold. So this will solve all of these equations. So introducing these k coordinates has solved k equations out of your full set of structure equations. And the holding those coordinates constant puts you onto a submanifold. So you get a topological condition from the Frobenius theorem. And let's see. That's what we have here. D of omega looks like omega over here. In fact, everything's in involution here, but omega is in involution. So there exist coordinates, 6 of them, such that I can write omega AB as omega A B. What do I want to call these? Let me call them CB and call these things lambda DC. These 6 coordinates, these are antisymmetric in AB. They're basically rotation matrices. These are Lorentz transformations. These are local Lorentz transformations, those coordinates. Those are coordinates on a fiber. So this is in involution. If I hold these lambdas constant, these omegas vanish. This gives 0. That's determining a cross section, and I have DEA equals 0, and these E's now span a submanifold. So these are some E mu A dx mu, mu running 1 to 4, and because D of those is 0, these coefficients are constant. I can choose them to be, or let's see, actually, I can just integrate this. EA is just some D of some XA, because D of it vanishes. All right, and that means that I have an orthonormal frame on this manifold that's also a coordinate frame, which means that it's a flat space and flat 4-dimensional space together with the metric. All right, so orthonormality, I'm going to define using a matrix that I know is left invariant by Lorentz transformations. And I've built space-time. Right, so by taking the quotient of the Poincare group by the Lorentz group, I actually construct space-time Minkowski space as the quotient manifold. And it's a fiber bundle. And the fibers are Lorentz transformations. So the object I've built this way is Minkowski space with local Lorentz transformations, all lying inside the Poincare group. So this is what we've done with like a bit of machinery that's new to you, okay? But and you know, when I teach this to my students, Eli, you know, I repeat this 4 or 5 times. So I don't expect you to really digest this.
Or 7 or 8, you know. Just a few
Sorry,
times.
Eli, didn't hear.
Oh, I just said, you know, or 7 or 8 times, you know.
Yeah. Yeah, don't hesitate to ask again about this. And it is written up in the Gage Theory book, so you can read about this too. But yeah, you know, these are complicated ideas. I don't expect any of you to get it on first hearing, but you see there is a general way to move from a group and a subgroup, a Lie group and a Lie subgroup, to a fiber bundle. And we can use that for a lot of different purposes. It gives us a manifold with fibers. The fibers are the subgroup. So we can control the symmetry of our model this way. All right, so Now, there's a generalization of this. We need one more step to make this really interesting. We change the connection. Any way you like. We're going to change the omegas and the E. Something different. Okay, so these equations don't hold anymore. But we can still compute them, but what's going to happen is, we're going to get some additional 2 form over here. And we're going to get some additional 2 form over here. Like this. This still lives on a fiber bundle if we put a restriction on these additional 2 forms. What we say is they're horizontal. That is, they're invariant under lifting, right? We talked about lifting on a bundle, which cross section. So we don't let these depend on the cross section. An equivalent way to say that is that integrating this connection around any closed loop is independent of lifting. All right, Stokes' theorem tells us that that will get this thing if we integrate around it. If we integrate this around a loop, we're going to get that thing integrated over some area. So it doesn't matter what cross section we do, as long as we require these 2 objects to be horizontal, which in this case, where we've taken the quotient of Poincare by Lorentz, horizontal means in these E directions. And so you show that this means that you can expand this A, B, C, D just in terms of the E's, no omegas. So in general, a 2 form on this bundle would be quadratic in the E's and the omegas. Horizontality means, oh, no omegas. Then it wouldn't be independent of lifting. So by this horizontality restriction, we guarantee that we've preserved the fiber bundle structure. We still have local Lorentz covariance of everything in sight. This 2 form is called the Riemannian curvature 2 form. This is the Riemannian curvature. This T is the torsion. Often in GR, that's taken to be 0. And you can show that for a wide range of Lagrangians that T equals 0 is a valid solution. So if we say, all right, suppose we let these indices run instead of P running, this running from 1 to 4, suppose we let it run from 1 to n and let that n-dimensional space have arbitrary signature. We've now written the equations for any Riemannian geometry in any dimension and any signature. Just in an hour, When I was a grad student, Chern did this in 20 minutes. And then it took me the next several years to figure out exactly what was going on there. But it was worth the investment. This is very powerful stuff. So this gives us tools for considering huge classes of geometries with various symmetry. Now, let me show you what we're going to do. Instead of just Poincare, let's put an SU3 here. And instead of just Lorentz, let's put an SU3 there. So we're going to take the quotient of Poincare cross SU3 by Lorentz cross SU3. So now, in addition to these equations, we're going to have some SU3 potentials and whatever the structure constants are for SU3. And if we generalize it, there's going to be a field strength here. This is the Yang-Mills field strength for SU3. And because the Poincare generators all commute with the SU3, it's just a direct product here. What we're going to do when we generalize this connection and make those horizontal, we're going to take this T and this R to be 0. So we're back in Minkowski space, with the difference that we've constructed an SU3 bundle over Minkowski space. And SU2 and U1. And now we're looking at the standard model. So by taking Poincare across SU3 across SU2 across U1, taking the quotient by Lorentz across the standard model symmetry, we build a fiber bundle, which we can immediately generalize to include the Yang-Mills field strengths. And we're doing standard model gauge theory. Okay, the next step then is to write an action that actually gives us the field equations that make sense. This gives us the objects of the theory. It's easy to make a list of the objects that are relevant here, but then it's up to us as physicists to write an action in terms of those objects, say the Einstein-Hilbert action for the curvature. And once we've done that, we've got a physical theory. Now, if you want to do general relativity, okay, all you do, you set T to 0, you write the Einstein-Hilbert action for R, and you can solve these equations for the connection every bit as well as you solve for the Christoffel symbols and the metric in general relativity. So this is actually a very nice way to do general relativity. You get the Bianchi identities out as the integrability conditions for this more general equation. This is called the Carton equation. The Carton equations are the ones with the curvatures and field strengths added in, where we've changed the connection, made the field strengths horizontal, and that gives us some fields on a flat or curved spacetime. If you want to do the standard model in curved spacetime, just let R be non-zero and F be non-zero, and you're doing the standard model in curved spacetime. Now, just you got to quantize it and all this stuff, right? That's whoops. I guess we lost Eli for a minute here. Welcome back, Eli.
Sorry about that. Computer problems.
Yeah, that happens. Don't worry about it. Let's see. So let's look at the Yang-Mills bit of this. I forget what I said last time about Yang-Mills theory. Did I actually write out the Yang-Mills field strength? I think I did. It's in the notes from the preceding chapter. Did the commutator of a couple of SUN covariant derivatives? Seemed to me we got through all of that, but I don't remember for sure. You got it? Yeah, so yeah, one of the last things that I would have written is something like here's what I have in the notes. FA alpha beta. Remember, this guy's a 2 form, right? That's the alpha beta here. Okay, so yeah, now I'm remembering going through this. So I have the connection beta comma alpha minus the connection alpha comma beta. And then we have the structure constants, ABC, B alpha, B, C, beta. So we developed this by taking the commutator of two covariant derivatives, which we constructed more or less by hand. But this approach gives us a connection. And the this F here in this Carton equation is a two-form. So I can write it as a two-form on space-time, and dx alpha wedge dx beta. That's all equal to the rest of this d ai plus 1/2 ci j k a j wedge a k. This is identical to that. I think I may have given that as an exercise, in fact, just to let you get a little familiarity with this notation. Did I put an exercise in here? Well, I'm not seeing it, but maybe I'll go back and stick one in. I think I worked it out myself, but yeah, read about it and do that. If you just expand everything in an alpha beta. So this D is dx alpha partial alpha a I beta dx beta with a wedge product between the forms plus all that stuff. So that term is I could write the two form automatically anti-symmetrizes things. Beta a alpha with a half, then dx alpha wedge dx beta. Once you explicitly anti-symmetrize everything, this is always anti-symmetric. So I've made this anti-symmetric by anti-symmetrizing. And you can anti-symmetric, this is automatically anti-symmetric. So the halves go away and you end up with this expression in terms of A instead of B, but otherwise exactly that. So the form of the curvature is immediate from the Carton equations, right? That minus 1/2 right here, right? That tells you the coefficient here. And it comes out right this way. That is, this is not a covariant derivative, by the way. It's, yeah, the covariant derivative would have to have two of these factors. I mean, there is a covariant derivative that looks very similar. It does not have that minus 1/2 that the Carton equation has. So you want to be careful with that. You know, I'm happy to talk with any of you anytime about all this stuff. You can read about it in the Gage Theory book. You know, this is the kind of tool I use all the time. It's not hard to write an action, the Yang-Mills action, in terms of this, this two form. Uses the third thing, the Hodge dual. It's just Fi wedge the Hodge dual of Fj, and you contract with the metric on the algebra is the Kronecker. So this is the F-squared action, just like the F-squared action of electromagnetism, right? Do this all for U1 and you can construct all of Maxwell theory, you know, right from that action. Now, let's see. There is an integrability condition. We can add sources. Let's see. I'm wondering, given your furrowed brows and distracted looks, whether I should go much more deeply into this. Can I clarify any of this for you? Or should we just move on and start talking about SU2 and SU3? That was non-committal. Come on, Guillermo, what do you want to hear about? You want to see conserved currents in this kind of theory, or do you want to start looking at the structure of those groups?
I'd like to see, wait, conserved currents and what?
Well,
Exactly.
okay, so, you know, this is the Yang-Mills action here, written in terms of these two forms. And you can add, just like in electromagnetism, you add in a vector potential with J. You can do that with these guys too. You just have an extra index on everything, like that. And you can show from the resulting field equations that J is conserved, even though it's a covariant derivative of J. It's a covariant divergence that vanishes. You can still show that it's conserved. So that's kind of cool. It's in the notes. Let's see, what does it take to do that? Yeah, I've confused you plenty. I could maybe you should just press deeper into this and confine all your confusion to one day.
Alrighty then.
Yeah, how about it? Seriously, what would you like to say? Let's see. You want me to say this all again? Would that help?
I'd like to. No, I mean, the current sounds really good actually.
Okay.
I want to hear that.
So let's do a little bit of physics with this. Let's see. Yeah. So what we want. Yeah, this equation gives the field strength, but and you know, I think I mentioned this before, but there are you can include more or fewer indices in a lot of these field theory expressions. And to really understand it all, it's probably a good idea to do it every possible way. Right? Put it in all the indices, put in no indices, see the patterns in different ways and convince yourself that, oh, this really is doing what I think it's doing. So let's talk in physical theory. So I've got some Yang-Mills field. I runs from 1 to capital N, where my symmetry group is SUN. And this is going to be D of N potentials plus 1/2 Cij, where these are real structure constants, A, J wedge, A, K. So that's my Yang-Mills field. And now I do some physics. I say, all right, my Yang-Mills action is going to be, I think 1/2 works nicely here. And I might want to call it 1/4 later. I forget. But what I want is Fi wedge the Hodge dual of Fi. And working out, that's a 4 form in 4 dimensions. This ends up being the contraction Fi alpha beta with Fi alpha beta, the usual, like the squared Maxwell, right? So for Maxwell, you would write 1/4 F mu nu F mu nu. That's what this is, just written in differential forms. And then I want to subtract, and let me get my normalization here. I'm going to put a structure constant, or not a structure constant. I'm going to contract the potential with N currents. This is a coupling constant. We can pull a constant out of A to adjust for units or the strength of an interaction, and that's quite useful to do. So if I vary A inside any curvature constructed this way, I get D of the variation of the connection plus a half ci jk del a j wedge a k plus 1/2 ci jk a j wedge del a k. Now this is minus del a k wedge a j, and the structure constant is minus ci kj. If I interchange those two indices, the minus signs go away, and this term is exactly like that term. So it cancels the half. And now a connection can be written in the adjoint representation as, let's see, let's see. I think which way I want to do these. Yeah, I could get two of those just as well. Maybe that's what I want to do, because I want to define a structure constant Cijk on a connection 1 form. This gives me a connection 2 form. Let's see, what do I want to call that? I'm going to call that omega ik. It's just another form of the connection with an extra structure constant on it. But if I use that, and let me use this second one here, then I have d of del ai plus the half goes away, and then I combine this with the aj to give an omega ik del ak. And that now looks like a covariant derivative. This is what I was alluding to before when I mentioned the importance of this half. This is not a covariant derivative of A, but something like this is. There's no half here. And so I can write this as the covariant exterior derivative of the variation. And that is a derivation, right? It's the usual derivative plus a connection on some vector. So now, when I vary this action, let's see, do I want to do, yeah, let me do one more thing with this covariant derivative. This as a quick aside while we're talking about it. If I take, right, if I look at, all right, this was the structure equation. This is the Carton structure equation. So minus a half Cijk aj ak wedge product plus fi. The Poincare lemma, basically this is taking two partial derivatives and anti-symmetrizing them. That always gives 0. So d squared of anything is identically 0. But what I get over on this side is Cijk d of aj wedge ak plus d hitting the second a, aj wedge d ak plus d of f. Sorry to cram it so tightly here, but I don't want to erase this yet. So we have 0 is what? Well, I have now these two are the same as well. And I can, right, if I interchange jk here, I get a minus sign. Hang on. If I, this time, dA is a 2 form. So AK and dA commute, right? So when one form passes a 2 form, there's no sign. So when I interchange these, it changes the sign and I get two of these. So I can write this as CIJK, drop the two. And then the AJ, that's actually my connection omega IK. And then this DAK, I'm going to substitute from the original structure equation here. Minus 1/2 CIJK AJ wedge AK plus FI, all with that connection, plus DFI. Now, there are three terms here. I have a DFI, then I have, sorry, this omega IK, better make it M here. That was summed on DAK. Yeah, I need to change the index to get that right. So plus omega I M F M. Then this is minus 1/2 C M J K. Then this omega, remember, is C I L M A L wedge A J wedge A K. And that anti-symmetrizes the JKM. Sorry, JKL, like this. That's identically 0 because that's the Jacobi identity of the original group. And what we're left with is the covariant exterior derivative of the curvature. So this is a generalization of the Bianchi identities. If we had done this for the Riemannian geometries, we would have found both of the Bianchi identities as the integrability conditions for those equations. Okay, so here we have an integrability condition, which it's fair to call this a Bianchi identity. Just keep in mind what it is. You know, within Yang-Mills field theory, I don't know what people call that. I just think of them all as Bianchi identities or integrability conditions. So now we have this same covariant derivative, and we see that the variation of the field strength is the covariant exterior derivative of the variation of the potentials. That makes varying these things fairly straightforward. Okay, so varying A in the Yang-Mills action, I'm going to get the variation of F, but we just showed that the variation of F is D of the variation of A, wedge star F, plus I'm going to get Fi wedge, and now you sometimes have to be careful here whether the Hodge dual commutes with the variation. It does in this case. I've run into theories where it doesn't, so you have to worry a little bit. But then this ends up being the Hodge dual of D of del A. And then here we get minus G del A wedge J. So let's see. Let's just put another in this. Now, it's not too hard to show that for two forms, a two-form wedge with the dual of a two-form is that you can throw the dual over onto the other one. at worst with a sign, since these are two forms, it's going to be plus. So if I put this dual over onto that F using that lemma, I just get two of these, and that's why I put the half in the first place. So I'm going to get D of del AI, the two's gone, wedge the dual of Fi, minus, let's make it plus G, if I interchange these, Ji del AI. That's fine. Okay, and so now derivatives obey the Leibniz rule. So even though this is a covariant derivative, D of a product, dAI wedge star Fi, is equal to D of del AI wedge star Fi. This is a one form, so I pick up a minus del AI wedge D of star Fi. And this is D of a four form. And for, let's see, D of a four form is a scalar, right? Okay, think when you take the covariant derivative of a scalar in general relativity, it's just the partial. So the same is true for a four form or an n form in n dimensions. The exterior covariant derivative is the same as just the exterior derivative. And so when we integrate these things, this is a surface term. This is a simple exterior derivative of 1, 2, 3 form. Yeah, that's right. And integrates to a surface integral where we require the variation of A to vanish. So we're going to be able to throw out the surface term. This is just integration by parts where we have a vanishing boundary term. Okay, so what that says.
Why is that second term a minus sign?
Here?
Yeah.
Because this is a one form. So the exterior derivative acting on a product of forms gets alternating signs. Okay, so we get a minus sign when the D passes the A. That D is a one form operator. So so what we can say is D of del AI wedge star Fi is actually equal to del AI wedge D of star F. So we don't get the usual minus sign here integrating by parts because we're varying a one form. And they've got my signs. Oh, I should have left this alone. Yeah, let me write this the other way. Minus del AI wedge Ji. Okay, so here's the variation. We're going to set the variation of the action to 0. So 0 is equal to the integral. I've integrated this term by parts, so I can pull out my del AI. And I have D of star Fi minus G Ji times the arbitrary variation. And so the usual way here, I conclude that D of star Fi is equal to G of Ji. And now if I if I take a dual of this, yeah, I suppose I could have done this a little, in a little bit tighter way, but dual of J. This is that star J is the usual current because okay, here this needs to be a 4 form. A is a 1 form, so this is a 3 form. Now, what I could have done in the first place is to write that as the dual of a 1 form. So if J is a 1 form, its dual is a 3 form. And then I would have the dual all the way through here. And this would be a dual. So a double dual comes back to 1. And that's a little tighter. Star D star is the covariant divergence. All right. Yeah, that's you know, check my differential forms notes in the Gage Theory book. I'm sure I proved that. So star D star is divergence, and so this is just like Maxwell theory. Star D star of F, the covariant divergence of our SUN gauge field is a coupling constant times the current. So this all follows the pattern of the Maxwell theory. Now, to show the that current is conserved, let me see, what did I do to do that? Yeah, I had to go through a little work to do that. But what you need is the Richie identity. Now, the Richie identity is what you get in general relativity if you take the commutator of 2 covariant derivatives. So in general relativity, some space here. You may have seen that if I take the commutator of 2 covariant derivatives, okay, that's going to give me derivatives of the connection, but this is a tensor operation. And acting on a vector has to give a tensorial stuff over here. And what it gives is, well, up to the sign. I have a feeling there's a minus sign here, but you get the Riemann curvature out on the left side. And this is actually a nice way to generate a form for the curvature. If you do this in differential forms, let's see, there's a similar thing for our gauge covariant derivative here. So if we have d alpha d beta acting on, well, now we need some object in the algebra, and this is going to end up being, let's see, well, what is it actually? Yeah, you get yeah, you get this V, you get a structure constant, C I J K V J F K. So you still get a linear combination of the curvature, plus or minus, and we can work that out. So to prove that current is conserved, that star D star of that current is 0. Let's look at what we need. Yeah, okay, this is going to work out. So if I apply star D star to star B star of F, that's going to be G star B star of J. Okay, so I'm just taking the field equation and I'm applying the divergence operator to it. Now, this divergence operator, the Hodge dual of the Hodge dual, it's you're ready for a term. involutive automorphism, you know, it squares to 1. Right. So you take the dual, of the dual, and you're back to where you were. So this is just star of D of star of F. And that's our divergence. Okay, well, the cool thing here is this covariant derivative squared is the commutator, right? Because this is, right, we can think of this as a dx alpha d alpha wedge a dx beta d beta. So dx alpha wedge dx beta d alpha d beta. The two form anti-symmetrizes things. So I can write this as 1/2 dx alpha wedge dx beta of the commutator of two covariant derivatives. And that's a curvature. So look, we better work this one out carefully. So now let's let this d squared operator, by which I mean d wedge d, by which I am perfectly correct in saying is 1/2 dx alpha wedge dx beta times a couple covariant derivatives. I want to let that act on, it's actually fine to let it act on anything in sight. Now, in fact, we're going to be interested in its action on star F, but let's just look at it on any Lie algebra vector. All right, a single Lie algebra index is a vector in the Lie algebra. Whatever else it might be, it's a vector in the Lie algebra. So d squared on that is 1/2 dx alpha wedge dx beta. Then we have d alpha d beta of omega I minus alpha beta interchange. And now the covariant derivative, let's see. You've got to be a little bit careful here because it depends on what kind of object this is. Let omega I be a P form. Then D acting on it, you know the way you have a plus sign if you're differentiating in GR a contravariant vector, a minus sign if you're differentiating a covariant vector, tangent or cotangent vectors. The connection works the opposite direction. Well, a similar thing happens with differentiation of a P form. You have to be careful with your signs. Your signs alternate. And so let me see. D of omega I. All right. I don't have to use the indices. This is D of d omega I, and then I have a -1 to the P I have to include here. And then I have that connection form with this omega. So omega J wedge, unfortunately I chose omega IJ. The 2 index one is the connection, right? It's the structure constant on A. Now I do this again. So I get D of all of this, D omega I plus -1 to the P. Then I get a D omega J wedge omega IJ. And then this thing is a P form. So D passing it is going to, oh, wait. No, two steps, sorry. D of that. And then I have plus -1 to the P plus 1. Because now the derivative of omega becomes a P plus 1 form. And then we have this P plus 1 form, D omega, better use a new index, plus -1 to the P omega J wedge omega K J, all wedge omega IK. Okay. You with me? Yeah, okay, good. So so now I take D of all this, right? D squared is always 0. So that term goes away. Then we have -1 to the P, D omega J wedge omega IJ. And then passing a P form, I get another -1 to the P. That's going to just give +1. So we'll have plus omega J wedge D omega IJ. Then here we have -1 to the P plus 1, D omega K wedge omega I K, that's these two. And then we have minus the P times the P plus 1, 2 omegas J wedge omega K J wedge omega I K. Okay, these two differ by 1 sign. So the D omega K cancels. And what I'm left with is omega J wedged with D omega IJ minus omega K J wedge omega I K. And there's a structure constant on F. This is exactly F. Let's see, should I prove that? Let's see, okay, so F I is D A I plus a half C I J K omega J omega K. And if I put a structure constant on that, let's put C K I J on it. Then F I C K I J is right. This is on the center index here. That makes that an omega. So this becomes just D omega K J. And then we have to worry about this term, a half C. Oops, I'm going to make this MN so I don't collide indices. So C K I J with C I M N omega M wedge omega N. Okay, so then what I need is the Bianchi identity. Okay, the Jacobi identity. Well, they're the same. C I M N C K I J. Let me think where I want the indices here. I may want to do it the other way. Let's see. C. Huh. Which way do I want these? Let's see. I M N C K. All right. I'm going to make it Ji with a minus sign. So interchange those two. So I'm summing on this last one. The antisymmetric part of that is identically 0. So if I write that out, I have C. Let me see here. C I M N C K J I plus C I N J C K M I plus C I J M C K N I is identically 0. That's the Jacobi identity. I don't have to subtract the 3 antisymmetric perturbations because each of these, this is antisymmetric on MN, this on NJ, this on JM. So this is, you could write this as 6 terms, antisymmetrizing the 3 indices. It would boil down to the same thing. And now, the one of these that I've got, Kij, this I summed there, okay, ought to look like one of these things. Here's the I summed on, should have left it where it was. Yeah, I can do that. If I make this IJ, make this IM, make this IN, I've still anti-symmetrized. I still anti-symmetrized the JMN. So now Kij here and IMN there. So this term is the one I've got. What I actually have is, right, I have a half of that term. So it's equal to minus a half that term and a half of that term. So I can write the thing I've got as minus these 2 terms. Minus 1/2 CINJCKIM plus CIJMCKIN. Okay, and now I've got what I wanted. If I just find some space to put it. So what I've got is FICKIJ is equal to D omega KJ plus a half. This is now minus a half of all that. Minus 1/2 of quantity CINJCKIM plus CIJMCKIN omega M wedge omega N. Shout if you can't see that. That's omega M wedge omega N here. Okay, now that combines these two because, let's see, now where do I want the sign here? Right. If I interchange those two, I get a minus CKMI. So I'll just write this again. D omega KJ minus 1/2. And now I'm going to put the M and the N both in the center. And I've got MN first, so hang on, let's see. Oh, yeah. no sign there, one sign there. Yeah, this term, if I interchange both pairs, I get CIMJ omega M wedge CKNI omega N with no change. On this first one, I need to interchange the MN, so I get a minus, but I only need to bring the M in the middle to have the same thing. So this term gives the same as that, and the 2 is gone. And so finally, F on a C is D omega K J minus omega I J omega K I with a wedge. So that's exactly what we got down here. So, you know, you check things, right? All right, so we didn't have that identity. We needed that identity. So what do? You prove it. So, all right, what we had here was D of some P Lie algebra value P form. And what we get down here is that it's equal to that same P form wedged with all of this, which is, we just proved F. Let's get my indices right here. I better use a K with a C. I is the free index up. Then F is subtract is in the middle and J. So there's the equivalent of our Richie identity for Yang-Mills theory. Now that's even what I got last time in the notes. Okay, so now, look at all this stuff. What can I erase here? Let me come up here. So the thing we were doing, we had said star D star star D star F equals G star D star J. Right, you were working on that identity. The two Hodge duals give 1. So now we have a star and then D squared of star F. Well, the D squared, that's still a Lie algebra valued something form. So we are going to get, right, in place of omega J, we have star F and J on it. And then that's wedged with FK and contracted on a CIKJ. And that's the divergence of our current. Okay, but star FJ wedge FK. Remember the term I quoted about interchange of the dual? That's going to be the same as FJ wedge star FK. And one of these is a 2 form. So that's the same as star FK wedge FJ. So this thing is symmetric on JK. This is antisymmetric on JK. Identically 0. And that proves the divergence of the Yang-Mills current is 0. And I know we've used a whole bunch of new tools. Did I tell you the story about Chern? I mean, I told you he did this stuff in 20 minutes. He was giving a lecture on invariants that come out of general relativity. This was a
like some seminar in grad school. And he, in the first 20 minutes, he derived all the equations of general relativity of Riemannian geometry this way. You know, he's doing all this fancy stuff with differential forms, much as we just did. He did it for general relativity. So, you know, he would be working with the quotient of Poincare by Lorentz and modifying the connection and so on. I hadn't really seen it before, but it convinced me it was worth learning. So I did. And, you know, it's really nice. Okay, so let's see, how are we doing? So what is it, 2 and 2.25? Yeah, well, let me give this summary. And you know, maybe that's enough for today. I've raked you guys over the coals, right? This yeah, not easy stuff. There's a lot of new stuff here, but it's written down and it's explained in more depth in the Gage Theory notes, which are on the quantum field theory page now, the current one. So learn as much of this as you want. We're not going to use a whole lot of this to develop the standard model or string theory after that. So, you know, this is not something you have to digest to, you know, be on top of this class. But it's neat stuff. You can do a whole lot with it. Yeah, let me run through the summary just as I have it in the notes, just to so you can see what we've done. So we start with Poincare cross SUN. We take the quotient by Lorentz cross SUN. That gives us the Maurer-Cartan structure equations. For the Poincare group. And for our SUN gauge field. So generalize the connection. That's going to introduce the field strength of the curvature. You know, we could also generalize. We could generalize these if we wanted to work in curved spacetime. This quotient is our 4-dimensional spacetime manifold. If we do not do these, then that manifold is just Minkowski space, just flat spacetime. So, so we're not going to do that. If I call this one a tilde and drop the tilde by generalizing it, then we have the A is -1/2 Cijk, a j wedge a k plus the algebra value 2 form. And this is the Yang-Mills field strength. And that is a 2 form.
these E's are actually an orthonormal basis. I could also write this in an orthonormal basis, AB, EA, wedge, EB. That's the solder form, the Vierbein, lots of names for that. I don't know if you've been introduced to that in relativity yet or not. All you're doing when you use this is you're choosing the basis for your cotangent space to be orthonormal instead of just some coordinate basis. Like it's a vector space. Why not choose an orthonormal basis? In any case, we write an action half F I wedge star F I minus G. Which way did I write it? A first. A J I. And that then implies that star D star Fi is G J I. Oh, this has a Bianchi identity. EFI is identically 0. That's the integrability condition for this equation. And then we showed that this in turn implies star D star Ji equals 0. So there we've got the all the essential underlying equations for the for any Yang-Mills theory. Yeah, the group doesn't even have to be SUN. It could really be any of the algebra, and we could do the same thing. Let's see, did I leave anything out here? Yeah, along the way, it was convenient to define a 2-index connection using a structure constant. That's just fine. That's just choosing a particular representation for the Lie algebra. It's called the adjoint representation. And it's explicit enough that it's a really handy form to use. So there is an exercise here. Oh, using that identity on the F's, proving that star F wedge F is the same as F wedge star F. But just if you want to learn this stuff, just reproduce it, right? Try to work through it on your own, expand all the differential forms, see what's happening with the derivatives and the anti-symmetrizations. The way to get this is to just, try doing it. Do it for SU2. Write it all out for SU2. The generators are I times the Pauli matrices, or maybe minus I over 2 times the Pauli matrices if you want your signs nice. And just see what happens. See that it gives you some things you maybe recognize or expect. So anyway, that's probably enough for today. I'm still working on the notes on this next section. I'm pretty much done with the SU2, and I think I've posted that much. I'm still fussing with SU3, and I've pasted a whole bunch of junk at the bottom because I'm trying to use some old notes and merge them in, and so at some point it gets a little messy, but I'll try to get that all sorted out before next Monday. Yeah, maybe later this week I'll get an updated set of the notes posted. They're complete through what we've talked about today. So any questions? Anything I can help you with? If you're working through this stuff this week sometime and something's weird or not working, pop me an email, let me know, and I'll help you with it.
Let's see. Yeah, I should stick in some problems. I haven't stuck in many exercises yet, but you need to be working with this stuff to really get it. So work with it, really get it. It's cool. All right. You good? Any questions? Okay. Kevin, you good? Eli? Good. All right. Okay. Then I'll see you guys next week. All right. Be in touch if you have questions.
Mhm.
Okay. Till
All
next
right.
week. See ya.
And
Right,
I'll
see ya.
see you tomorrow. Do you have a time that works for you tomorrow?
Oh, usually kind of mid-afternoon, 3 or 4. Let me think. Tomorrow's Tuesday. Oh, yeah, not too late. We have some friends coming over later. So, yeah, anything particular work for you? Probably 2 or 3 is going to work well.
That's what I was thinking, is around 2 or 3. Either of those
All
three.
right. Yeah, I was thinking about our project. It's a good project.
Mhm.
We may get a phys letter out of it.
That'd be cool.
Yeah.
Yeah.
So, yeah. See you then. Let's see. I should be able to make it by 2.
Okay. I'll plan for 2 then. Let me know.
All right. Yeah. If I get a late start tomorrow morning, I will. I'll send you a text.
Yeah. And if we have to, like, Wednesday would also work well for me. So.
Okay. Yeah. Tomorrow. There are a couple things I got to get done tomorrow. So. Yeah. The morning's a little busy, but okay. Let's say 2 for now, and I'll let you know.
Sounds good.
All right, Eli. Take care.
You
Hope
too.
you're feeling better.
Hopefully.
Yeah. Those Oreos should help.
Yeah. My mom, I came up from my parents' house recently and she sent them with me. So.
Oh, nice. Nice. Yeah. It's good food, those Oreos. All right. I'll see you tomorrow.
See you tomorrow.